Hi, good morning. In this video, we prove theorem 2.9.1 that let X be an n-dimensional vector space and X star be its algebraic dual. Then dimension of X star is equal to dimension of X is equal to n. അതായത് ഒരു സ്പേസ് n-dimensional ആണെങ്കിൽ അതിന്റെ algebraic dualum n-dimensional ആയിരിക്കും. Okay, let us see how this can be proved. So given that X is an n-dimensional space, so let B is equal to x1, x2, x3, etc. xn be a basis for capital X. ഇനി ഇത് basis ആണെന്ന് പറഞ്ഞാൽ എന്താ അർത്ഥം? Every x belongs to capital X can be uniquely represented as a linear combination of x1, x2, x3, etc. xn. That means these are unique scalars such that x is equal to alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn. What we want to show is dimension of x star is also n. അതിനെന്താ ചെയ്യുക? We have to produce a basis for x star having n elements. And we proceed like this. So നമുക്കറിയാവുന്നത് capital X ലെ ഏത് x എടുത്താലും that x has a unique representation of this form. Now we define n functions fi from x to the scalar field capital F defined by fi of x is equal to alpha I. So what is alpha I? X നെ ഇങ്ങനെ ഒരു യൂണീക്ക് റെപ്രസെന്റേഷൻ ആയിട്ട് എഴുതുമ്പോൾ ആ റെപ്രസെന്റേഷനിൽ xi യുടെ കോഎഫിഷ്യന്റ് ആണ് fi of x. So is the definition clear? Fi of x is the coefficient of xi in the unique representation of x as alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn. So we have n functions. So let capital F is equal to collection of all these functions f1, f2, f3, etc. fn. Then we can see that these fi's satisfies this condition. That is fi of xi is equal to 1. അതായത് xi യെ ഈ ഫോമിൽ എഴുതുമ്പോൾ xi can be written as 0x1 plus 0x2 plus etc. plus 1xi plus 0xi plus 1 plus etc. plus 0xn. So xi can be written in this way, in this unique way. So fi of xi is the ith coefficient or the coefficient of xi in the representation of this xi, that is 1. And fi of xj fi of xj, see xj can be written as 0x1 plus etc. plus 0xi plus etc. plus 1xj plus etc. plus 0xn. In this representation, fi of xj is the ith coefficient, means the coefficient of xi. Coefficient of xi is 0. So this. So our so defined functions fi I from 1 to n satisfies this condition that fi of xj equal to 1 if I equal to j and equal to 0 if I not equal to j. Now these are n functions. Now we can show that this capital F is a collection of linear functionals, of which 50% is already done. The members of capital F are functionals because they are functions from x to capital F, the scalar field. Okay, so we will use another symbol for this. Let k. Let k be the set f1, f2, f3, etc. fn, and then k is a collection of functionals because they are functions from the vector space to the scalar field. Now we want to show that this is linear. So how we can show that this is linear? Now each fi is linear. Oh, what is the condition for linearity? So we say a function fi is linear if fi of alpha x plus beta y is equal to alpha fi of x plus beta fi of y. അതിനെന്താ ചെയ്യുക? അതിന് ക്യാപിറ്റൽ എക്സിലെ രണ്ട് എലമെന്റ്സ് എക്സും വൈ എടുക്കുക. So let x and y belongs to capital X. So this x has a unique representation of the form alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn, and y has a unique representation beta 1 x1 plus beta 2 x2 plus etc. plus beta n xn. So therefore fi of x, so by the definition of fi of x is the coefficient of xi in the unique representation of x as a linear combination of x1, x2, x3, etc. xn. So fi of x is alpha I, and fi of y is equal to beta I. Now alpha x plus beta y is equal to x ne alpha കൊണ്ട് multiply ചെയ്യുക and add it with y multiplied by beta. So what we get is, simplify ചെയ്ത് എഴുതുകയാണ്, that is alpha 1 plus beta 1 x1 plus etc. plus alpha I plus beta I xi plus etc. plus alpha n plus beta n xn. Therefore fi of alpha x plus beta y is equal to, ഈ alpha x plus beta y ഇപ്പോൾ നമ്മൾ ഇതാ x1 x2 x3 etc. xn ന്റെ ലീനിയർ കോമ്പിനേഷൻ ആയിട്ട് എഴുതിയിരിക്കുകയാണ്. അപ്പോൾ fi യുടെ ഡെഫിനിഷൻ അനുസരിച്ച് ഇങ്ങനെ എഴുതപ്പെട്ട ലീനിയർ കോമ്പിനേഷനിൽ xi യുടെ കോഎഫിഷ്യന്റ് ആണ് fi. So this is alpha I plus beta I, and now this is equal to alpha, and our alpha I is fix, alpha fix plus beta I is fiy. So this condition is satisfied, therefore fi is linear. Therefore each fi I from 1 to n is a linear function. അങ്ങനെ ക്യാപിറ്റൽ എക്സിൽ ഡിഫൈൻ ചെയ്തിരിക്കുന്ന ലീനിയർ ഫംഗ്ഷണൽസിന്റെ കളക്ഷൻ ആണ് എക്സ് സ്റ്റാർ. അതുകൊണ്ട് FIകളെല്ലാം ഇവിടെ വന്നോളും, എക്സ് സ്റ്റാറിൽ വരും. സോ ഫോർ I equal to 1 2 3 etc. n. Therefore this f1 f2 etc. fn are n elements of x star. FIs are linear, FIs are functionals. So these are n linear functionals. Therefore these are n elements of x star. Now we can show that, this k is equal to set f1 f2 etc. fn forms a basis for x star. So for that we have to prove two things. We need to show that this k spans x star, and to show that this k is linearly independent. So first we show that k spans x star. അതിനെന്താ ചെയ്യുക? x starലെ ഏത് എലമെന്റ് എടുത്താലും അതിനെ ഈ f1 f2 f3 etc. fn ന്റെ ലീനിയർ കോമ്പിനേഷൻ ആയിട്ട് എഴുതാൻ കഴിയും എന്ന് പറയണം. അതിന് x starലെ ഒരു എലമെന്റ് എടുക്കുക. ലെറ്റ് f belongs to x star. Therefore f is a linear functional. Therefore for every x is equal to alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn, fx is equal to, f is linear. So by linearity, so this is f of alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn. f is linear. So this is equal to alpha 1 f of x1 plus alpha 2 f of x2 plus etc. plus alpha n f of xn. Okay. Now f is a linear functional. Remember that. So f is a function from x to capital F. അതുകൊണ്ട് ഈ fxiകളെല്ലാം സ്കേലേഴ്സ് ആയിരിക്കും. fx1 is an element of capital F, fx2 is an element of capital F, etc. fxn is an element of capital F, and you set f of xi is equal to beta I. So f of x1 is beta 1 is a scalar, f of x2 beta 2 is a scalar, etc. And we already observed that what is this alpha 1? x നെ ഇങ്ങനെ യൂണിക് ആയിട്ട് റെപ്രസെന്റ് ചെയ്യുമ്പോൾ അതിലെ x1ന്റെ കോഎഫിഷ്യന്റ് f1 of x ആണ്. That is alpha 1. So that is the definition of f1. So we repeat, x നെ x1 x2 etc. xn ന്റെ ലീനിയർ കോമ്പിനേഷൻ ആയിട്ട് എഴുതുന്ന സമയത്ത് ആ ലീനിയർ കോമ്പിനേഷനിൽ x1ന്റെ കോഎഫിഷ്യന്റ് ആണ് f1 of x, x2ന്റെ കോഎഫിഷ്യന്റ് ആണ് f2 of x. So this is f1x beta 1 plus this alpha 2 is f2 of x, f of x2 നെ നമ്മൾ beta 2 എന്ന് വിളിച്ചു, plus etc. plus fn of x beta n. So this is beta 1 f1x plus beta 2 f2x plus etc. plus beta n fnx. And this is beta 1 f1 plus beta 2 f2 plus etc. plus beta n fn of x. So f of x is equal to beta 1 f1 plus beta 2 f2 plus etc. plus beta n fn of x. Therefore, f is identically equal to beta 1 f1 plus beta 2 f2 plus etc. plus beta n fn. So that means every member of x star can be expressed as a linear combination of, so this is a linear combination of members of K. Therefore, K spans x star. Now it remains to show that K is linearly independent. K is linearly independent. So for that we consider a linear combination of members of K equal to 0. So let alpha 1 f1 plus alpha 2 f2 plus etc. plus alpha n fn equal to 0. So this is a 0 vector, means this brings every element of capital X to 0. See, f1, f2, f3 etc. fn are linear functionals. So alpha 1 f1 plus alpha 2 f2 plus etc. plus alpha n fn is also a linear functional. So this is a function, this is a function from x to the field, and this function is 0, means this is the 0 functional. So this brings every element of capital X to 0. So in particular, this brings every basis vector xi to 0. So applying this to alpha 1 f1 plus etc. plus alpha n fn of xi equal to 0 for all I from 1 to n. We know that f1 of xi, when we remove this bracket, this is alpha 1 f1 xi plus alpha 2 alpha 1 f1 xi plus alpha 2 f2 xi plus etc. plus alpha I fi xi plus etc. plus alpha n fn xi equal to 0. We know that f1 xi 0, f2 xi 0 etc. ഇതിനകത്ത് 0 അല്ലാതെ വരുന്ന ഒരു ടേം ഇതേ ഉള്ളൂ, and this is 1. ഇതെങ്ങനെ 1 ആയി? fi യുടെ ഡെഫിനിഷൻ, xi യെ ഒരു ലീനിയർ കോമ്പിനേഷൻ ആയിട്ട് എഴുതുമ്പോൾ അതിനകത്ത് xi യുടെ കോഎഫിഷ്യന്റ്, that is 1. So this implies So this implies alpha I equal to 0 for all I. A linear combination of f1, f2, f3, etc. fn equal to 0 implies all scalars equal to 0. Therefore, k is linearly independent. So thus, k is equal to f1, f2, etc. fn is a linearly independent spanning set for x star. Therefore, k is a basis for x star. And that completes the theorem, because in this case, therefore, dimension of x star is equal to n, the number of elements in this basis, and that is equal to dimension of x. That is a theorem.